In this lecture, we will talk about Anova, which is analysis of variance, and this is given in chapter 11 of our textbook. So let us look at one example, which is illustration 2 in the book. And in this example, some data is given. So there are three varieties of wheat. Okay, so you can think there are three types of seeds, type A, B, and C. Okay, and an experiment is done to determine if there is a difference between these varieties of seeds. Okay, if there is a difference between variety A, B, and C. And for that, what was done was there were four plots of land, 1, 2, 3, 4. And in each plot, each seed was sown and production was measured. Okay, so for seed A, we got 6, 7, 3, and 8. Okay, whatever, maybe the units. Uh, and from seed B, we got this production, and for seed C, we got this production. Okay, and based on this, we have to determine if there is a difference in variety of seeds. Now, if we represent this data graphically, as you see here, for seed A, you see there is a big variation from 3 to 8. So just because of various random factors which are not part of the experiment, because these different plots, they may have different type of soil, or other factors may be different, but see, this data is from 3 to 8. Okay, from 3 to 8, and the mean of the data, if we work out, that is 6. For B, the data is from 3 to 7. You see here 3 to 7, the mean is 5 if you calculate mean of this. And for this one, the data is from 3 to 5. The variation is less here. Okay, it is from 3 to 5, and the mean is 4. Okay, so you see now there is a variation even when we are using the same seed. Okay, there is huge variation 3 to 8 even when using the same seed, or here from 3 to 5 even when using the same seed. And there is also a variation of the mean from seed to seed. So here the mean is 6, mean is 5, mean is 4. Okay, but all this variation could be due to random reasons or could not be due to random reasons. Okay, so in Anova, what is done is the following. One is we can calculate the sum of squares total. Okay, which is abbreviated as SST, sum of squares total. So what is done is calculate the mean of all of this data. Okay, so just add all of these 6, 3, 6, 7, 3, 8, 5, 5, 3, 7, and divide it by the number of entries here. So you get the mean, and then you see the deviation. So mean here turns out to be 5. If you calculate the mean of all of this data, that turns out to be 5. And deviation of each one, deviation for this will be 6 minus 5, and we square that. Okay, similarly 7 minus 5, square that. 3 minus 5, square that. 8 minus 5, square that. So like that for all the values we do. So you can call that sum of squares total, because in calculating this we have considered all the data. So we do that, it turns out to be 32. Okay, and you already know we calculate this sum of squares when we have to calculate the variance. If we divide this with the degrees of freedom, we get the variance. Okay, so it turns out to be 32 here. That is sum of squares total. We have considered all the data here. And now we can also calculate sum of squares in two other ways. One is called sum of squares within group, or you can also call it sum of squares within a sample. It is abbreviated as SSW. So sum of squares within a group. And within a group means now we are just looking at one group at a time. We are looking at just this group, say A. This is a group. We are looking at this. And for this, we are calculating sum of squares. Okay. So for that, you can, for the moment, you can forget about B and C. Just look at A. And the mean here is 6. You add all of these and divide by 4. You'll get mean here is 6. And now see the value will be 6 minus 6 square of that plus 7 minus 6 square of that, 3 minus 6 square of that, 8 minus 6 square of that. Okay, so you have calculated sum of squares within the group. So do that for group A. Same thing, do it for group B. Same, do it for group C and add all of these. Okay, that will be called sum of squares within the group. Okay, for example, if you want to do that for group C, mean is 4. Okay, so the sum of squares within the group will be 5 minus 4 square plus 4 minus 4 square plus 3 minus 4 square plus 4 minus 4 square. Okay, that will be the sum of squares within the group. Okay, so that is done here. Sum of squares within the group, in which in this case you look at one group at a time and calculate sum of squares for that group and just add sum of squares for all the groups. Okay, that will be sum of squares within the group SSW. And another sum of square is calculated, that is called sum of squares between groups. Okay, it is abbreviated as SSB, sum of squares between groups. And while calculating this, we look at, you see I've written here, we look at the group mean and the total mean. Okay, the group mean and the total mean. Okay, for example, the group mean for this group, okay, the group mean here is 6, and the total mean, the mean of the entire data, we calculated that previously, that was 5. Okay, so you will do 6 minus 5 square. See, group mean is 6. 6 minus 5 square for this value. Okay, for this value also we'll do 6 minus 5 square, because for any value you have to look at the group mean and subtract the total mean from that and square of that. So 6 minus 5 square, 6 minus 5 square, 6 minus 5 square, 6 minus 5 square. So effectively 6 minus 5 square will be counted 4 times. And that way we have considered all the entries of this A type. Okay. Similarly, now we go to B. For B, the group mean is 5. Okay, and the total mean is 5. So 5 minus 5 square for each of these, we'll do that 4 times, add those. And similarly for C, the group mean is 4 and the total mean is 5. So 4 minus 5 square, 4 minus 5 square, will have to do it 4 times. Okay, so that will be called sum of squares between groups. So you see here, 4 times 6 minus 5 square plus 4 times 5 minus 5 square plus 4 times 4 minus 5 squares. Okay, it turns out to be 8 here. Okay, so there are 3 things here again. One is sum of squares total, in which we have considered all the data. We have the overall mean, and from each value we subtract the mean and the squares and add. Another is sum of square within group, in which case we take each group at a time and calculate the sum of squares and add all of those. Other is sum of squares between groups. And I explained, in this case we use group mean and the total mean. okay, the difference of those, and square that. For each value we'll have to use that. And it turns out that the sum of square total, okay, sum of square total, which is kind of the total variation in the data, turns out to be equal to sum of squares within the group plus sum of squares between the group. Okay, it turns out to be like that. It can be proved, but we are not interested in that here. So effectively, see, what is done is in ANOVA is the total variation, this SST, this total variation is split into two parts. One is within the group, okay, and other is between the group. Okay. Now, within the group is, you can say, due to the random factors. Okay, the variation within the group is due to random factors, and the variation between the groups is due to difference in variety. Okay, so for example, say, let us say if SSB turned out to be 0. Okay, if SSB turned out to be 0, then the situation here will be the mean of each group will be same, and that will be equal to the total mean. So effectively there is no difference in mean. Okay, uh, but here SSB is not 0, it is 8. And this, so you get the idea. This SSW represents variation within the group, which is due to random reasons, and SSB represents variation between the groups, which is due to difference between the variety of seeds in this particular case, and their relative magnitude. Okay, their relative magnitude is used to ascertain if there are difference in varieties. So for example, if SSB turns out to be very large, SSB turns out to be very large, and say SSW is small, okay, that means that there is a difference between the groups. So the ratio is important, but before we calculate the ratio, we have to take the degree of freedom into account. So let us look at that also first. uh, so the degree of freedom for SST is n minus 1. Okay, we added n terms here. The degree of freedom is n minus 1. The degree of freedom for SSW is n minus k, where n is the total number of items in the sample and k is the number of groups or samples. Okay, it is n minus k. And the degree of freedom for SSB is k minus 1. Okay, and if we add these two degrees of freedom, we get the degree of freedom for SST. Okay, we have to take these degrees of freedoms into account to calculate our statistic, and then compare that with some critical value. Okay, as we did for chi-square test also, to ascertain if there are difference, if the differences between varieties are significant or not. Okay, so for that we construct what is called an ANOVA table. So we write here source of variation, and again in ANOVA we have split our variation into two sources. Okay, between samples and within samples. So this is SSB and this is SSW. Okay, so you write the source of variation, and then sum of squares, we calculated it, it turned out to be 8 for SSB, 24 for SSW. Then we write degree of freedom. For SSB, the degree of freedom will be k minus 1. We have three like actually we have three varieties, three types of seeds here, uh, or three groups here, you can say, or three samples. All these terminology are fine. So 3 minus 1, it will be 2, and degree of freedom here will be n minus k. We have total 12 you see data points in the table. So 12 minus 3, 9. Then we calculate mean sum of squares. So we divide sum of squares by respective degree of freedom. So 8 by 2, that is 4. And here it will be 24 by 9, that is 2.67. So those are mean sum of squares. And after that we calculate F ratio. Okay, that is defined as MSB over MSW. So this is mean sum of squares between groups divided by mean sum of squares within group. Okay, so it will be 4 divided by 2.67 here equals 1.5. Okay, so the idea here is if the differences are significant, okay, then the F ratio will be large. And if the differences are not significant, if they are just due to random variation, then the F ratio will be small. Okay, but what do we mean by small or large? We'll have to read a critical value from the table. And for that, table 4 is given. Let us go to the book and see that table. So this is table 4A. It says critical values of F distribution at 5% significance level. And table 4B, this is critical values of F distribution at 1% significance level. Okay, now depending on the problem, if the problem says 1% significance level, we'll go to this table. If it says 5% significance level, we go to this table. And see, for reading this table, we are given 2 degrees of freedom here. This V1 and V2. Degree of freedom from 1, 2, 3, 4, and V2 also 1, 2, 3, 4. So we have 2 degrees of freedom. And then we'll read some critical value from the table. And let us see how that is done by referring to our example. See, here we had 2 degrees of freedom. Degree of freedom for between samples, it was 2. And degree of freedom within sample is 9. So we have 2 degrees of freedom. One is 2 and other is 9. Okay. So we have to read the value of F, okay, corresponding to 2 and 9. But is it going to be 2 and 9 or it is going to be 9 and 2? Okay. So let me show you what I mean. See, this is 2. We can take V1 is 2, V2 is 9. So we get the value is 4.26. Or if we take V2 as 2 and V1 as 9, we'll get a different value. Okay, so which value we'll have to read? So for that, what is done is we write as F V1 V2, and V1 is the degree of freedom for greater variance. Okay, V1 is the degree of freedom for greater variance. So we see this mean sum of squares. Okay, here this value is 4, this is 2.67. Which one is greater? 4 is greater. And corresponding to this, what is degree of freedom? Degree of freedom is 2. Okay, so the degree of freedom for greater variance is 2, and for the smaller is 9. So we are going to read F29 from the table. So read V1 is 2 and V2 is 9. Corresponding to that, you read this value is 4.26. Okay, this is critical value of F. So critical value is 4.26, and the value we got, the F ratio was 1.5. It is less than the critical value, so it will fall in the acceptance region. So we just accept H0, the null hypothesis, which is that the difference in weight is insignificant. Okay, so that is the process for this Anova test, which is called one-way Anova. Okay, one-way Anova. And I will refer you to the book where the steps are given. You should go through this section. Okay, here it gives Anova technique, and the steps are given, which I already explained to you. Okay, you can go through these steps. I already explained, but here they are given in some mathematical notation. Uh, and everything is summarized in this table, table 11.1. Okay. See, the source of variation between sample and within samples. Okay, and this is for SS, degree of freedom, this is MS, and this is F ratio. And uh, uh, between samples, if we have to calculate the sum of squares, it is going to be, see, I told you, when we are looking at SSB, then we are looking at the group mean and the total mean. Okay, this x1 bar, this is group mean, and x bar bar, this is total mean. Okay, so the group mean minus total mean, square of that, and n1, these are the numbers uh, that are in that particular group. Okay, the number of values in that particular group, because you have to add the same thing for each value. Okay, so like that we are doing for each group, so this becomes SSB. Okay, and this is SSW. For SSW, I told you that you look at one group at a time. So this x1 bar, okay, this is mean of group 1, and then this x1i, okay, these are all the values in group 1. So you are taking this deviation uh, for all the values in group 1, and then squaring them and adding them. So this is for a particular group. Then you do the same thing for each group, and these are the corresponding degrees of freedom. These are corresponding mean squares, and then this is F ratio. Okay. And another thing here is, if you add SSB and SSW, you will get SST. Okay, the sum of squares total, which has degree of freedom n minus 1. Okay, this is called Anova table. Uh, there is also, see, this method which is given in table 11.1, this is called direct method. Okay, for one-way ANOVA, direct method. If you're doing this calculation, it is called direct method. There is also a shortcut method for one-way ANOVA, and that is given in this section. You should go through this, page 260 in the book. And what is done here is, uh, first we add all the values. See this sigma xij. Okay, all the values that are there, just add them, and it is called T, like in a sense some sort of total. Okay, so take the total of the values of individual items, call it T. Then work out a correction factor which is defined as T square by n. Okay, it is called correction factor. N is the total number of items in the table, with the total number of items. And then SST we can calculate by using this formula. It is sigma xij square, so square of all the values in the table, add them, minus this correction factor T square by n. Okay, this is SST. SSB we can calculate by this formula, sigma Tj square. Now Tj is total for each group. Okay, we are taking one group at a time. So Tj is the total for a group, square of that divided by number of items in that group. Okay, and we are adding that for all the groups. Okay, minus this correction factor, this is SSB. And if we do SST minus SSB, you will get SSW. Okay, just the difference of these two, that is SSW, that is what is done here. So if you use these formulas to calculate SST, SSB, SSW, okay, that is called like a shortcut method. and the previous one was a direct method. But regardless of whichever method we use, eventually you need to make this ANOVA table and calculate F ratio. Okay. Okay, so I will suggest you do this example, illustration one, uh, that I showed you, by using both methods yourself. You can make sure you can do it. Okay, so we already talked about direct and shortcut method. You should know how to apply these methods for this one-way ANOVA. Okay, now there is another which is called two-way ANOVA. Uh, in two-way ANOVA, data is classified on the basis of two factors. Okay, the previous one was called one-way ANOVA because data is classified on the basis of just one factor. In our example, that factor was seed variety. Seed variety was A, B, or C. Okay, it was classified on the basis of just one factor. If it is classified on the basis of two factors, it is two-way ANOVA. For example, if data is classified by the variety of seed and also by the variety of fertilizer. Okay, there are two factors now, seed and fertilizer. So it will be called two-way ANOVA. And let us say there is production in a factory, and the number of units that are produced are classified on the basis of the machine that is used and also the labor that is used, if the labor is skilled or unskilled or semi-skilled. So there are two factors here. So in that case, it is called two-way ANOVA. And the method for two-way ANOVA is slightly different, and we are going to look at table 11.3 in the textbook and illustration 2 in the textbook for two-way ANOVA. So it is given here, ANOVA technique in the context of two-way design, that is two-way ANOVA, when repeated values are not there. And the process is summarized in this table, table 11.3. It is very similar to one-way ANOVA, but there is a small difference. So when we construct this ANOVA table for two-way ANOVA, see the source of variation. Now you don't have two sources of variation. We have three sources of variation here. Okay, this is sum of squares between columns. Actually, now let me show you an example before we get to this. Yeah, yes, this illustration 2. So here you see there are three varieties of seeds, A, B, and C, and there are four varieties of fertilizers, W, X, Y, Z. Okay, and data is given. When you use seed A and fertilizer W, the production is 6 metric ton. So like that, the production is given. Okay, so this will come in the category of two-way ANOVA. And this is two-way ANOVA without repeated values. Without repeated values means that if we are using seed A and fertilizer W, we only have one value in the table, 6. It is not that the experiment was repeated with seed A and fertilizer W. So we had multiple values here. Okay, so this is two-way ANOVA without repeated values. Okay, so now in this case, you see, because there are two factors, uh, unlike one-way ANOVA where you had only one factor. So we were saying our categories in the previous example were like seed A, seed B, seed C. Okay, they were these columns. Now we can say our variety is like seed A, seed B, seed C. So these columns, and also these rows also, fertilizer W, fertilizer X, fertilizer Y, fertilizer Z. Okay. Uh, so that's why the source of variation uh, is one is between columns. Okay, we are not saying now uh, uh, that between groups. Okay, because groups can be columns and also rows. It is two-way ANOVA. So source of variation one is between columns. Okay, and when we are calculating between columns, it will be based, the sum of squares will be based on this formula, uh, where this Tj represents the total for the column. Okay, total uh, for a column, and you are adding this for all the columns, and the degree of freedom will be number of columns minus 1. The mean square will be this SS between columns over this degree of freedom. Okay, that is one source of variation between columns. Other will be between rows. Between rows. Okay, now again the same thing, but now see this summation is for the row, like this Ti square over Ni. So this is total for row number 1, square of that divided by number of items in row number 1, plus do the same thing for row number 2, for row number 3, like that. Okay, minus this correction factor, and degree of freedom will be r minus 1, number of rows minus 1. Mean square, we just divide this uh, with this, so you get this mean square. Okay, so these are two sources of variation. Then there is SST. uh, SST is given by this formula, uh, and the degree of freedom for SST will be number of columns times number of rows. Okay, which will be the total number of entries, the total number of items minus 1, total number of items minus 1. Okay, then apart from these three, there is another source of variation, which is residual or error, and this we can calculate as SST minus, see, if we add these three sources of variation, we'll get SST. Okay, so the source of variation for if the source of variation is residual or error, the sum of square will be from the total, from this SST we subtract both of these, so this will be the residual, and the degree of freedom associated with residual will be c minus 1 times r minus 1, and the mean square for this source of variation will be this one. Okay, now again see the idea, because there were two sources of variation, uh, this term is due to variation between columns. Okay, this term is due to variation between rows, and the last term is due to actually due to random variations. Okay, so we have to take the ratio of this with this, and that will give us 1f ratio. Okay, similarly we take a ratio of this with this, that will give us second f ratio. We are having two f ratios because there are two factors. It may be that both factors are important, or maybe just one factor is important. So we have two f ratios here. Okay, and then we will compare both of these f ratios with the critical value from the table. So that is how this two-way ANOVA is done when we don't have repeated values. Okay, now in this particular example, you should go through this example illustration 2, and it says at 5% significance level, we have to uh, we have to determine if the differences are significant. Okay, so there are two questions: whether there is a difference between seed varieties, or whether there is a difference between fertilizer varieties, or both. Okay, so see the way this, so they have taken this shortcut method. uh, so the correction factor is first determined, then SST, then SSB for column, then SSB for row, and then the residual. Okay, and then this table is constructed. We have all these SS values. You have this degree of freedom, then this mean sum of squares by dividing SS with degree of freedom, and we have these two F ratios, 4 divided by 1 and 6 divided by 1, that is 6. Okay, so these are our F ratio, and then this last column, you see these are the critical values of F we get from the table. So for this one, see, for this F ratio, there were 2 degrees of freedom corresponding to 4 and 1. 1 degree of freedom is 2, other degree of freedom is 6. Okay, but for which degree of freedom we have more variation? You see, for this variation is 4, for this variation is 1. So this is more. So we are going to read F26. So F26 from the table, which is 5.14. Okay, and similarly for this F ratio, uh, corresponding to 6 and 1, we have 2 degrees of freedom, which are 3 and 6. Okay, for which degree of freedom we have more variation? See, 6, this is more variation than 1. So for 3 degree of freedom we have more variation, so we are going to read F36. So this is what we read from table. Okay, now now you compare this F with the critical value. So this F is less than the critical value, and this F is more than the critical value. Okay, so that means that for this one, you are going to accept the null hypothesis. So which will be that the difference between columns, or you say the difference between seed varieties, are not significant. Okay, difference between seed varieties are not significant. But here we see this F ratio is larger, so it will be in the rejection region. So we'll say that the difference between varieties of fertilizers is significant. Okay, so that will be the conclusion. So difference between seed varieties is not significant, but difference between fertilizer varieties is significant. So which fertilizer we are using is making a difference here. Okay, that is the idea. So please go through these couple of examples from this chapter.